Hello everyone, I'm Maria Thakur, and today we're going to talk about accessing resources. So in a course like this, that is fundamentals in ecology, why should we study foraging decisions? Well, essentially, foraging decisions influence the shape and outcome of food webs. So if you notice the food web on the left here, there are all these arrows that connect one trophic level to another, right? Predators that are eating prey. But not all species are connected by these arrows, which means that in ecosystems that have multiple species interacting, not everybody is eaten by everyone else. And so we need to think about the fact that animals don't eat everything they encounter. They may share the same habitat, and their foraging decisions are not random, which means how energy is flowing through the environment depends on who is eating who. So what should organisms eat? Well, we can understand and predict foraging behavior in a few ways. And the first way I want to teach you is the optimality approach. This means that behavioral decisions have been shaped by natural selection and is shaped towards an outcome. And that outcome is to maximize the benefits and minimize the costs. So I'm going to start with an observation that was made by David Lack in 1956. He says, "It was to be expected that swifts would allow insects that were too large for them to manage, and that extremely small ones would not be taken. But a more subtle selection for size was revealed by analysis of the meals. In fine weather, the meals consisted chiefly of insects 5 to 8 mm long, but in poor weather, 2 to 5 mm long." So this observation is him observing birds making foraging decisions. And those decisions aren't random. I'll continue. Now, insects 2 to 5 mm long are commoner in fine than in poor weather, and are more numerous than larger insects in all types of weather. Presumably, in fine weather, when larger insects are plentiful, swifts can collect the meal more quickly if they do not go out of their way to catch smaller kinds. In bad weather, on the other hand, insects are so scarce that the swifts cannot afford to be so selective. What I've underlined here is a decision that swifts are making to actually avoid some food while searching for others. So can we use optimality theory to predict what animals should eat? Absolutely. Let's think about the foraging birds example just now, the observation. It had a decision that the bird needed to make, what to eat. Should it eat one type of prey of a certain size or more types of prey with different sizes? It had a currency in there, which is what should the foraging achieve? In most cases, animals are trying to maximize energy gain over time. And it had some constraints, right? Constraints like processing constraints or cognitive constraints or temporal constraints. So for example, the observation described that the birds could not fit large insects in their mouth. That's a processing constraint. So let's begin with the simplest model of optimal foraging theory, diet choice, which is what to eat and what not to eat. Suppose a predator in this environment encounters 2 prey types, and he's moving through the environment to encounter them. These 2 prey types differ in these key ways. The larger prey, in blue here, has an energy value of E1 and a handling time of H1. The smaller prey has an energy value of E2 and a handling time of H2. Handling time refers to how much time it takes the predator to catch that insect, chew it, and get the resource value into its gut. So actually get the energy accessible to it. So it takes some time. Once it encounters the prey, it still has to catch it and eat it. So now I'm going to set this up such that the aim of the predator is to optimize profitability. This means it wants to get prey that has the highest energy over handling. So the first thing it needs to do is to rank prey based on profitability. So in this example, I'm going to say that the large prey is more profitable than the smaller prey. So E2 over H1 is greater than, E1 over H1 is greater than E2 over H2. This is what we're optimizing here. When I say that we're working on an optimality approach, what we're saying is that the predator wants to maximize the benefit, minimize the cost, maximize the energy over time. Now, if predators want to maximize overall rate of energy gain as it's foraging, then when it encounters a prey, should it eat it or not? Because we've already set up this ranking that the larger prey is more profitable than the smaller prey, the predator should always eat prey 1 when encountered. There's no circumstance by which prey 1 wouldn't be more profitable. So then the question is, when to eat prey 2? If the predator is always eating prey 1, is that enough for it, or should it include prey 2? So let's think about when, under what circumstance should a predator eat prey 2? It should eat prey 2 only if the gain from eating prey 2 exceeds this, the gain from rejecting prey 2 and searching for the more profitable prey 1. And so now we have to include a new term in our optimality approach here, right? Which is the search time for prey 1. So as the predator is moving, it's got to decide whether the gain from eating prey 2 right here, when it encounters it, exceeds the gain from rejecting prey 2 and moving on and looking for prey 1. So now let's add S1 into the equation. The gain from eating prey 2 is just as profitability measure, right? Energy over handling time. The gain from rejecting prey 2 and searching for more profitable prey 1 is the energy gained by eating prey 1, including the search time for that prey. So now we have a new inequality. We can arrange this inequality to put the one thing that differs, which is search time, on one side. So for a predator, it should eat prey 2 only if this inequality is met, that there's enough prey 1 in the environment that the search time for prey 1 exceeds this, the energy and handling time relationship with the two prey. So let's take this verbal description of what a forager needs to do or a predator needs to do and articulate the outcomes, right? So here are the predictions of optimal diet choice. Foragers have the choice to specialize, which is to eat prey type 1 only, which is the most profitable prey, or generalize, eat more than one prey, eat the profitable one and then subsequently less profitable prey. The decision to specialize depends on the abundance of the profitable prey and not the abundance of the less profitable prey. This is a really interesting prediction because for us to set up that inequality, we're saying that the predator has to ignore the less profitable ones and look for the more profitable prey. The switch between these two, between specialization or generalization, occurs suddenly when S1 exceeds this inequality. Okay. So what is this general prediction of optimal diet choice? When overall food density increases, lower ranked items, meaning less profitable items, are excluded from the diet, even if they were accepted before. So this is like you being at a buffet or me being at a buffet and seeing its whole array of food. As long as the thing that has the highest profitability is available, we should actually ignore everything else. So as food becomes more available, foragers become more selective. Now, as with every model, we must think about assumptions. We're assuming that the forager can assess the value of the food upon encounter. So it needs to know what the energy value is and the handling is. handling time is for that food as soon as it arrives. The forager needs to know the array of different foods available so that it can rank it, right? Because it has to accurately rank prey according to E over time. And that time here I'm generalizing, right? But so far I was talking about handling time. We're also assuming that the forager searches randomly. Now, in the natural world, as we watch foragers make decisions about what to eat, sometimes we notice that foragers make mistakes, meaning it includes less profitable prey items in their diet, despite the fact that there's enough of the profitable prey in the environment. Does this mean that the optimal foraging theory is wrong? No, it doesn't. What it means is that we have to adjust the strength of our assumptions. Right? So let's look at these three assumptions again and think about how realistic they are. Right? It's unlikely that foragers have perfect knowledge of the environment and therefore perfect knowledge of the food options. It takes time for foragers to learn. So as we're watching them, maybe they're still learning what food options are available. Right? Natural environments are also changing and often unpredictable. So even if the predator has learned what is profitable in the environment and what arrays of food are available, if the environment changes, the forager has to learn again. And finally, animals actually search more efficiently than we predict, than we assume in models like this. What I will say here is that we actually can take optimal diet choice models and include terms to address the fact that animals search efficiently or that there is a learning time associated with it. Okay, with this I want to stop and give you two follow-up readings. Right? The first is an empirical test of the optimal diet choice conducted by Krebs, published in 1977. It was a really elegant experiment done in the lab to determine if great-tit birds can determine what is profitable and what is not and make optimal diet choice as per our predictions. The second paper is one that evaluates the field. So it gives you a sense of when optimal diet theory holds and how we can adjust our models to make it more realistic in the natural world. Now, we've been talking about a forager that is moving randomly in space and encounters prey types and has to decide what to eat and what not to eat. But what about a forager that has to travel to distant patches of food? Then optimal diet choice is not the one to use to predict what to eat. Now I want to talk about the marginal value theorem, which was first proposed in 1976 by Chernoff and then later Parker and Stewart. Kalsinik in 1984 empirically tested this with starlings. So the question to ask here, if a forager or a predator has to travel to get to a foraging patch, then it needs to ask itself, how long should it stay before moving back to where it came from, like a nest, or moving to a different patch? Again, we want to optimize the decision here. So you want a forager that gets the most amount of energy given the time it spends in the patch. So if you look at this graph that I've drawn up here, when the forager arrives at the patch, that's this point at the origin. And as it's foraging in the patch, it's gaining energy. And this curve will continue to rise as it gains energy and then will eventually start plateauing. And it plateaus because it gets harder and harder to find prey the longer you're in the environment. This is why it's called the marginal value. It's harder to find prey as you're foraging over time. Note that for us to decide how long to stay, a forager could stop here, right? At which point it gets very little energy gain, but it spends very little time. It could stop here, where it gets a lot more energy, and it spent a long time. And this decision should be predictable. And it's predictable based on how long the forager took to get to that patch, so the travel time. So if we take this graph, which is a decelerating energy gain curve, and we consider travel time, how long the forager had to travel to get to the energy curve, the point that that slope intersects with the gain curve is the maximum energy gain, the energy divided by the total time traveling plus the total time foraging. This slope gives you the highest net energy gain. Anything less than that or more than that, any other curve would be either too much cost or too much benefit given the cost. So we can actually predict when a forager should leave the patch as long as we know this gain curve and we know travel time. So this point is optimal time spent in the patch, right here. So we can use the marginal value theorem to predict changes in behavior when conditions change. So for example, if travel time increases, in other words, if patches are further apart or the patch is really far away from the nest, then what we have to do is change the length of the travel time and connect that with the gain curve. And now we have a new optimal patch time. So optimal time to stay in a patch will increase if travel time increases. What if patches vary in quality? The forager was first foraging in an environment where all patches were good, which means the gain curve was this higher curve up here. And then something happened to the environment and all patches became poor. So the patches changed from being good to poor, at which point the gain curve itself has become lower than in the good patch. What should the forager do? Its travel time hasn't changed, but now the quality of the patch has. So we can start at the same travel time and now intersect that with the new gain curve in the poor patch. And what we find is that foragers now stay longer at a poor patch to make up for the travel costs. Again, as you'll notice here, all we're doing is manipulating pieces of information about the environment and asking if it influences foraging decisions. Now here's another scenario that's actually quite likely to happen in the real world, the natural world. If patches themselves vary in quality and the foragers have to visit both good patches and poor patches, it can't do what it just did, which is stay longer in the poor patch and leave sooner in the good patch. It now needs to create a hypothetical average patch. This average patch doesn't exist in the environment, but it's an average of the resources available to the predator if it considers both the good patch and the poor patch. And now we intersect our travel time with this average patch. This value now is the maximum net energy gain if the environment was a combination of good and poor patches. So the forager knows this, or we're assuming the forager knows this, and he takes that slope and brings it up to the good patch, brings it down to the poor patch. This sets up a prediction that a forager spends longer in the good patch and shorter in the poor patch, because on average that would give it the highest maximum gain. So if patches vary in quality and foragers have to visit both, then each patch should be exploited until the gain rate within the patch drops to the average for the environment. So now let's take the marginal value theorem and come up with the predictions that we've just described. If travel time and the gain curve are known, then T opt, which is the optimal time in the patch, can be predicted. If there's more than one patch in an environment that varies in quality, all should be reduced to the same gain rate. If patches are already in poor quality when the forager arrives, then the forager should stay longer to make up for the travel time. When patches are far away, foragers should also stay longer. So distance to travel and the quality of the patch influences the decision to stay and how long. As with optimal diet theory, we have to be explicit about the assumptions of the marginal value theorem. The first one is similar to the one before. Each patch type is recognized instantly by the forager. So the forager arrives at the patch and knows if it's a good patch or a poor patch. Travel time between patches is known by the forager. The gain curve is smooth, continuous, and decelerating. Right? That allows us to predict with the tangent. And travel time between patches and set time within patches right now, according to the first model we set, have equal energy costs. We can of course change that and make the energy cost of travel higher than the energy cost of foraging. These are just adjustments to the model. Once we've built the basic model, we can add more parameters. So let me summarize optimal foraging theory in terms of diet choice and marginal value theorem. Both types of models use this optimality approach. And they both have three elements: a currency, constraints, and a decision variable. The currency for both was energy gain over time. The constraints involve processing constraints, right, temporal constraints. They don't have unlimited time. Right? Cognitive constraints, which means the predator needs to be able to recognize a patch or recognize a food type. And it has a decision variable. In the optimal diet choice models, the decision variable was whether to eat a prey type or not. In the marginal value theorem, the decision variable was how long to stay in a patch once it gets there. Now, because we're talking about optimality and we're talking about a trait-like behavior, we have to remember that natural selection has shaped this. So natural selection has shaped the foraging behavior of animals to maximize fitness. Now, you'll notice that we're not measuring fitness here directly. We have a proxy or a surrogate measure, which is the rate of average net energy intake, right? Energy over time. But the assumption is an individual that has a higher energy over time or a more efficient forager will have higher fitness. Now, with these two models, you'll notice that they both have energy over time as the goal here. But energy maximization is not the only goal. And this was an observation that first was described by Bilovsky in 1978, when he noticed that moose actually eat aquatic plants, even though they can get all the energy they need from eating terrestrial plants. So if moose were trying to achieve energy maximization over foraging time, then they would eat terrestrial plants and have all the energy required. However, we see that they also eat aquatic plants. And Bilovsky realized that moose needed sodium, which means that energy is not the only currency we should consider. So I want to now show you one last set of models. This is a set called Nutritional ecology, where we now think of food not just in terms of calories or energy, but in terms of the macronutrients that are required. And the two biggest macronutrients is carbohydrates and proteins. So what you see here is called the geometric framework of nutrition. Geometric because we're considering food in a graphical form. So imagine an environment that has two food types, food type A and food type B. Each food type has a specific ratio of carbohydrate to protein associated with it. And so if an animal ate lots of food type A, it would still get the same ratio than if it ate very little of food type A. But what it will gain is a lot more carbohydrates when it eats here and a lot more protein when it eats up there. Relative to food type B that has less carbohydrates but more protein. So an environment is made up of food types that have various macronutrient ratios. What needs to happen is for us to think about what is the best ratio of proteins to carbs that a forager needs to maintain the highest fitness possible. And so that we call an intake target. And this is the term that Robbenheimer and Simpson proposed when they created this nutritional framework. So the intake target is the amount and balance of protein and carbohydrates that an animal needs to eat every day to achieve maximal fitness. So suppose the intake target of a forager is there. Right? It needs that amount of carbohydrate and this amount of protein to achieve maximal fitness. For that forager, it can achieve that by just eating food type A. So it can spend all day eating food type A until it reaches this point. Foragers can also have intake targets that don't fall neatly on any of the nutrient rails, right? Which means either on food type A or food type B. Right? But it still falls within the nutrient space, so between both food types. Then what can it do? It can eat a combination of both A and B to achieve the intake target. So in this condition, the environment provides nutritionally complementary foods, and the forager can combine foods to meet its intake target. Now in some cases, a forager may find itself in an environment where its intake target is outside the available food options. So a forager right now needs a protein level that's here and a carbohydrate level that's here, but no food type will give it. So what it has to do when it is exposed to nutritionally imbalanced food, they have to resolve the trade-off by either over-ingesting some nutrients or under-ingesting other nutrients. This is called the rule of compromise. And I'll show you how it works here. Right? So what a forager can do is achieve the carbohydrate target, at which point it's eating less protein. And it can do this by eating food type B. Alternatively, the forager can achieve the protein target. And by doing so, it's overeating carbohydrates. Now, when this has been studied in the wild, including in human populations, right, achieving the protein target seems to be a driver for foraging decisions. So most likely what the forager will do is try and achieve the protein target, and in doing so, eat too much carbohydrates. And that too much carbohydrates can then be stored as excess in the body. So this is not ideal, but it does happen. So now how do we know that intake targets actually exist for a species? Here's an experiment that was conducted by Chambers et al. In 1995, where they had locusts in the lab. And the locusts were given powdered macronutrients that were in two different ratios. One, a high carbohydrate to protein ratio, which is the line, the steeper line here. And the other, which is a low carbohydrate to protein ratio. And what they asked by leaving these locusts free to feed was what was the balance of nutrition that was achieved by the forager. And they found that every day locusts would eat a carbohydrate to protein ratio that were similar, all in this tight cluster. This is the intake target for locusts. Right? If it didn't have a balance of protein and carbs, it would have been anywhere in the state space. Right? It could have eaten only one type of food or the other. But in fact, what they found is that locusts mixed the two food options until it achieved an intake target. This has also been seen in the wild. Nutritional ecology and the balance of macronutrients and micronutrients have been observed by foraging animals in the lab and the wild many times. Right? So here's an example from the wild. Grizzly bears eat salmon and fruit. That's the observation. And that's unusual if we think about calories only, because grizzly bears can get all the energy they need. In fact, they can get higher energy from eating salmon only. But for them to get the maximum mass gain, which means the highest possible fitness, it needs to have a ratio of protein to non-protein energy. And then to do so, it eats fruit in addition to eating salmon. So let me sum up this lecture. I've shown you 3 different types of models that describe optimal foraging. The first was optimal diet choice, where the animal was trying to achieve the highest profitability. The second was marginal value theorem, where we considered travel time for foraging. And finally is the nutritional geometry, which is the balance of macronutrients. And here I showed you protein and carbs because those are the most important macronutrients. But we can create geometric frameworks that include lipids or even micronutrients. What about plants? Do plants seek specific nutrients? Yes. And we can predict nutrient intake in plants. Plants need at least 14 essential macronutrients and micronutrients. And different species have different intake targets, which is the ratio of nutrients required for maximal fitness. So this ratio of nutrient uptake and the fact that it varies between species has consequences for ecological communities. It influences the survival of the species in an area. This will come up when you learn about niche later on in the course. It influences who competes with whom and who wins this competition. It influences ecological succession, which plants show up in an environment in what order. And it finally influences nutrient and elemental flow from one trophic level to another. So I'm going to end this lecture with 3 things to think about. Right? The first is, how can we make optimal foraging models more realistic? Right? Should we be adding costs or constraints in these models? Right? Can we vary other considerations, right, like travel time and search time? Second thing to think about is whether intake targets, which again is the ratio and amount of macronutrients required for optimizing fitness, should it and can it vary between individuals of a species? And if so, why? And finally, where and when would one expect nutritionally imbalanced food in the natural world? With that, we end accessing resources in this lecture. Thank you.